Heyo, welcome to a video about the motion of charged particles in two dimension. So this is a video talking about motion of our charges travelling through electric fields, but looking at the maybe vertical and horizontal aspects of their motion rather than just the vertical or just the horizontal aspects. So a charged particle moving at an angle to a uniform electric field experiences a force which affects both components of its velocity differently. The component of the velocity parallel to the electric field changes due to the electric force, and the component perpendicular to the field remains constant. In Stage 2 physics, you're expected to be able to compare the motion of a projectile in the absence of air resistance with the motion of a charged particle in a uniform electric field. So both of these types of motion are analogous in terms of how you work them out. You also need to be able to solve problems for the motion of charged particles that enter a uniform electric field perpendicular to the field, and you'll need to be able to solve problems for the motion of charged particles that enter a uniform electric field at an angle to the field where the displacement of the charged particle parallel to the field is 0. So charged particles travelling at an angle to a uniform electric field, I've just used theta here to represent angle. The velocity of particles parallel, this symbol here means parallel, to the field changes due to the electrostatic force. So in our diagram, I'm just going to get a different colour. The force lines will be travelling from positive to negative. And the velocity that the charge has that is parallel to the field will be impacted by the electrostatic force, which is in the same direction as the field. So that's this one here on the negative charge, this one over here on the positive charge. The velocity perpendicular, that's this symbol here, to the field remains constant as the electrostatic force perpendicular to the field is 0. So this force here is 0, so the velocity remains constant. This is similar to our projectile motion if we think about a projectile that's launched off, I'll just say the side of a building. The force due to gravity is downwards at every stage, but there's no force acting horizontally, so the horizontal force is 0. So that therefore means there's no acceleration horizontally, and therefore the velocity is constant. So it's the same with particles, or it's the same with the velocity of particles that is perpendicular to the field and therefore the electrostatic force. The motion of a charge moving at an angle to a uniform electric field is described using the equations of motion. So those equations of motion that we use for constant acceleration, we can use them in projectile motion, we can use them in linear motion, we can also use them in electric fields, or for charges in electric fields that are uniform. And this is because the acceleration is constant. So, as a work example, an electron enters perpendicular to a uniform electric field with a velocity of 4.2 by 10 to the 7 meters per second. The electrostatic force causes the electron to deflect vertically, as I think that should say it, not the, as it travels across the field. Calculate the electric field strength if the potential difference between the plates is 1 kilovolt. So to work this out, we just use E equals potential difference divided by distance between the plates. This will be 1 kilovolt, which is 1 by 10 to the 3 divided by 5 centimeters, which is 0.05 meters. And our electric field strength is going to be 2 by 10 to the 4 volts per meter. We then have to calculate the magnitude of the acceleration of an electron inside the field. So to do this, our rule for acceleration is the electric field times by the charge divided by the mass of the charge. Our electric field strength is 2 by 10 to the 4, as we just worked out, volts per meter. Then our charge of the electron is going to be negative 1.6 by 10 to the 19. And then our mass is going to be 9.11 by 10 to the negative 37, because that's the mass of an electron. Our acceleration, once you pop all of this into the calculator, is going to end up as 3.5 by 10 to the 15 meters per second squared. This will be negative, even though this is only asking for the magnitude. I'll just point out that the direction of the acceleration is going to be negative, and that's saying that the electron is going to go towards the positive plate. And because the convention is to take the direction that a positive charge would go, which is towards the negative plate, the convention is to take that as the positive direction. That is why the acceleration of the electron is negative and towards the positive plate. This question does just ask for magnitude though, so the correct answer for this question would just be 3.5 by 10 to the 15 meters per second. The next question wants us to calculate the time taken for the electron to travel the length of the field. So to work this out, we'll just double check what the length of the field was. So it is 10 centimeters here. So to work this out, we just use our rule for horizontal velocity, which we know is going to be constant. So that will just be velocity equals displacement over time. And we'll just rearrange this to get time is equal to the horizontal displacement divided by the velocity. The horizontal displacement is going to be 0.1 meters, because that's 10 centimeters, and the horizontal velocity is going to be our initial velocity, which was 4.2 by 10 to the 7 meters per second. So subbing those in, 0.10 divided by 4.2 by 10 to the 7, we will get an answer of 2.4 by 10 to the negative 9 seconds. So that's how long it's going to take for the electron to travel the full length of the field. The next question wants us to calculate the vertical deflection of the electron, and the vertical deflection is the same as the vertical displacement. To do this, we can just use one of our equations of motion, and these will be provided to you on your formula sheet. For this question, we'll use distance or displacement is equal to the initial velocity by time plus half the acceleration vertically, and that initial velocity is vertical, and then multiplied by the square of time. So we know our vertical velocity initially is going to be 0 because it's just entered the field with a horizontal velocity. It hasn't, at the instant that it enters the field, it hasn't been subjected to the electrostatic force, and of course it immediately is following. So the initial vertical velocity is going to be 0. That therefore means that we can get rid of this entire term here. We only have to now use the square of the time and then the vertical acceleration, which is what we worked out before. So vertical deflection is going to be half 3.5 by 10 to the 15, and then square of the time, which is 2.4 by 10 to the 9 squared. And then if you pop all of that in a calculator, you'll end up with 0.01 meters. So the vertical deflection is going to be 1 centimeter. If we were to say the direction, it would be upwards, and using our convention, that would be in the negative direction because that would be towards the positive plate. So now we've got a proton entering an electric field travelling at 1 by 10 to the 4 meters per second at an angle of 30 degrees above the horizontal. The plates are 5 centimeters apart, and the potential difference between the plates is 0.25 volts, and we need to calculate the horizontal velocity and the vertical velocity of the proton's initial velocity. So initial velocity is up here. Using trigonometry, I've done this in advance, we know that the horizontal component of the velocity is going to be v, or the hypotenuse, by cos 30. Because this is the adjacent side, we know that the vertical component of the velocity is going to be velocity or hypotenuse by sine 30, because this is the opposite side of the triangle. So horizontal velocity, BH, is equal to V cos 30. Therefore, VH, horizontal velocity, will be equal to 1 by 10 to the 4 cos 30, and popping all of that into a calculator will give you 8.66 by 10 to the 3 meters per second. For the vertical velocity, I'm just going to do it in a different colour when they're next to each other. This will be V sine 30, which will be vertical velocity is equal to 1 by 10 to the 4 sine 30. Popping all of this into a calculator will give you 5.0 by 10 to the 3 meters per second. So that's our horizontal velocity and our vertical velocities. We next have to calculate the vertical acceleration of the proton in the electric field. Now, to do this, we'll have to do 2 steps. In the previous question it was broken down for us, but now we need to recognise that in order to calculate the acceleration, we'll need to calculate the electric field strength, which is equal to the potential difference divided by the distance between the plates. The potential difference is 0.25 volts, and our distance is 5 centimetres, which is 0.05 metres. This means our electric field strength is going to be 5 volts per metre. To then calculate our acceleration, we use our acceleration formula, which is the electric field by the charge divided by the mass of the charge. Our electric field, as we just determined, was 5 volts per metre. The charge on a proton is 1.6 by 10 to the negative 19 coulombs, and our mass of a proton is 1.673 by 10 to the negative 27. Therefore, popping all of that into a calculator, we'll get an acceleration of 4.8 by 10 to the 8 meters per second squared. So that is how fast our proton is travelling. And this acceleration will be directed towards the negative, because that's the direction that a proton would be travelling in this electric field, or in any electric field. It would always go towards the negative, unless it's being acted on by, unless work is done on the proton, in which case it could travel towards the positive, but in this situation there's no work being done. So next, the proton exits the field after 2.1 by 10 to the negative 5 seconds. Calculate the vertical component of the velocity of the proton upon exiting the field. So to do this question, we can just use our equations of motion, and in particular we're going to use the vertical velocity final is equal to the vertical velocity initially plus acceleration by time. So vertical velocity final is going to be equal to the initial velocity. We'll check our initial velocity vertically, and that was 5.0 by 10 to the 3 meters per second. So back to here, 5.0 by 10 to the 3. Now we'll check our acceleration. That was 4.8 by 10 to the 8 meters per second. 4.8 by 10 to the 8 meters per second, and the time is given to us 2.1 by 10 to the 5 seconds. Therefore, popping all of that into a trusty calculator, we'll end up with a final velocity of negative 5,080 meters per second. So in other words, 5,080 meters downwards. I've just realised I forgot to include the negative for the acceleration there, so I'll just pop that in now. It's a bit of a shoddy negative, but I'm sure you get the picture. So what's happened is our velocity of our particle has started off in the direction on an angle. I'm going to go back to the diagram towards the positive, but the force is pointing towards the negative. So that motion is going to eventually shift back down towards the negative plate. Final question is asking us to calculate the resultant velocity of the proton upon exiting the field. So to do this, we need to work out our overall velocity by doing vector addition of the horizontal and the vertical velocities. Our horizontal velocity is going to be constant because there's no force acting perpendicular to the electric field. Our final velocity is what we've just found, and that's 5,080 meters per second. So our overall velocity is going to be this here, which is the hypotenuse. So to work the overall velocity out, we'll do some Pythagoras. Overall velocity will be equal to the square root of vertical velocity final plus squared plus velocity horizontal squared. This will be equal to the square root of negative 5,080 squared, and that will become a positive because we're squaring it, and then the initial horizontal velocity squared, which was 8.66 by 10 to the 3 meters per second squared. So all of that under the square root. Popping this into a calculator, you'll end up with an overall velocity of 10,040 meters per second. We still have to work out the direction because velocity is a vector. So we're going to work out the angle clockwise to the horizontal velocity. To do this, we'll use, I'm just going to write this on the bottom here, tan, and that's equal to the opposite to the angle, which is the vertical velocity final, divided by the adjacent to the angle, which is the horizontal velocity. Therefore, the angle is going to be equal to the inverse of these numbers, which is 5,080 and 8.66 by 10 to the 3. this is going to give you 30.4 degrees. So 30.4 degrees clockwise of the horizontal velocity.